Hello and welcome to my presentation. I'm David Winge from Synchrotron Radiation Research from Lund University in Sweden, and I work in the group of Professor Anders Mikkelsen. And here's the outline of my presentation, where I want to show you how we construct a neural network using nanowire neural nodes, and we make them communicate with optical signals inside a shared waveguide. So why do we want to do this? We want to create a small footprint network. So that's why we use nanowire devices. And as a realistic starting point, we use insect neural networks. They have low energy costs, and blueprints of navigational circuits actually exist with relatively few components. We use optical communication because photons are cheap, and with a growing number of interconnections, optical communication can be very efficient. So the biological work underlying this work is done by the group of Stanley Heinze at Lund University. So they have actually picked the brains of bees and ants and mapped out the neural interconnections of the bee brain, for example. Then the group of Barbara Webb have taken these results and produced a blueprint of a simple neural network based on the anatomical findings. So the group of Stanley Heinze, they have actually gone to the jungles of Panama, captured bees, and stuck the electron inside their brains. So, for example, they stick electrons inside the brains, hit the neuron, and then they put the bee inside this kind of arena, and here they can simulate, for example, forward flight and backward flight. And one example here for a neuron, simulating forward flight, they recorded almost no activity, while simulating backward flight, they recorded huge activity of this particular neuron that seems to be sensitive to backwards moving motion. And then they did this over and over again for 100 types of different neurons and 100 different bees. And using the anatomical maps of the bee brain neural circuits, the group of Barbara Webb actually constructed a neural network based on these results. So let me tell you about how this neural network works. So as the input layer, we have compass signals and speed signals. And as the next layer, we have the ring attractor layer, which is a recurrent network that communicates within itself, and its task is to keep track of the heading of the agent or insect. The next layer is a memory layer that stores the direction towards home. And then everything communicates to the end output layer, which is a steering layer that is capable of steering towards home once homing behavior is activated inside the insect. And this is an example of how it can look like. So the outbound journey is in purple here, and the inbound journey is in green. So what needs to be built to actually realize this in hardware? So the group of Barbara Webb, they constructed a Python navigational model that did this, but we want to build it. So this is a folded out plot of the neural network where the ring attractor layer is in the middle, and here we see the mapped out recurrent connections. So, and the strength of them, we see here that the opposite neural nodes have the strongest connection, whereas the neighboring nodes has very little. So to start with, we need to build one of these neural nodes, and each of them needs to be able to take input, inhibition and excitation, process the sum or difference between an activation function, and then output the result to the other nodes of the network. And in this work, we have decided to do only the ring attractor network, and we wait with memory capability to the future. So once we have constructed a neural node, we need to be able to customize the neural network weights like this. We need to specify that this weight should be stronger than this, for example, both inside the layer and to the next layers. And we have to minimize communication losses for this to be plausible at all. So what kinds of methods do we use? In order to design the neural node components, we use nanowire design. Then we use COMSOL modeling coupled to SPICE circuit simulations to assess our design. And from this we get the activation function of the neural node. Then we design the ring attractor as a whole and a waveguide, and then we assess this with optical modeling using a FDTD solver. This gives us a weight matrix that describes the intra-layer connection couplings. And then we plug everything back into the Python navigational model and see if it can perform successful navigation, like this example. So, nanowire design. We work in the III-V material system, and specifically with indium phosphide, aluminium indium phosphide. Those nanowires have shown to be very good absorbers. You can construct LEDs in this material system as well, or similar, and T-shaped nanowire structures have also been realized, which is very interesting for logical applications such as ours. And then we do COMSOL modeling coupled with SPICE circuit simulations, and we separate it like this. First we model on the subcomponent level in COMSOL. Phototransistors, nanowires and LED components, and then we fit our results to standard models for transistors and diodes, and then we can plug this into a circuit solver to solve the full component. To be able to use it in the Python computational model, we have to normalize the output as well at one point. Then we design the ring attractor and the waveguide and assess that using optical modeling. And as a final step, we plug everything back into the Python navigation model to see if it can actually work. So now I'd like to show you the result from our design. So we start by discussing the neural node component in some detail. So we designed this using a wide nanowire stem with a branched nanowire, and the stem consists of two phototransistors, one for excitation and one for inhibition, and these operate at two different wavelengths to be able to distinguish the different input signals. So when current flows through the excitation phototransistor and the inhibition is off, all the current will flow through the LED over here and then produce the output. When there is some inhibition, part of the current will be subtracted and flow out through the inhibition phototransistor. And the ideal equation would then, activation function will look like this, where the different current flows through the LED, and then we have a saturation current that is implied by using a large external load resistance to the circuit. And here we see how we divide the modeling into different subcomponents. We have two different phototransistors and a diode. We use these wide gap phototransistors since there is a larger band gap over here and a low band gap in the absorber region to achieve both detection and amplification in the same device. That makes it possible to keep the design as simple as possible. So here we have some results from the modeling. Here's a band diagram of the phototransistor where we see the wide bandgap emitter and then the low bandgap base and collector regions. We get some transistor looking results here, which we fit to transistor equations, and we do the same for the quantum well LED in the nanowire branch. So here we see a low bandgap region, which is actually indium phosphide surrounded by indium phosphide with a mil aluminum content, and here we see a plot of the internal efficiency that we get from this LED. We see that we need to operate it at quite high current density to get a reasonable efficiency. Then we take all the three parts and we couple it through SPICE simulations. And here we see the final results for the activation function. I put here the ideal equation that I showed you before, and this is then the actual result. We see here that depending on the inhibition current, you actually get different activation functions, and this means that the true activation function is actually an explicit two-dimensional function of both the excitation and inhibition signals, so we will have to take that into account later. We have a direct comparison here to the activation functions used by Stone et al., and we see that we match the ring attractor activation function pretty nicely. We have to incorporate a shift here as this one is centered around 0, and that we do by using a constant background signal. It's also possible for us to tune the slope by changing the driving voltage of the circuit, and here we see an example where we can do this quite easily and get a different slope. And this is important for future applications where you want to mimic different kinds of neural nodes with the same component. So to finish off this one, I would just like to show you two different activation functions by using identical phototransistors. Here we see a very little change when you change the inhibition current with respect to the actual difference. In the real case, when we have different phototransistors, we see a large shift in behavior when we change the value of the inhibitory current, keeping the difference constant. So this needs to be generalized to take the full results into account. Moving on to the network design, there's a few key points. So thin nanowires possess a giant polarization anisotropy, and you can use this because the emission rate for the dipole directed along the branch is strongly favored over the other directions. So this actually shapes the emission into almost a dipole shape, and it sends most of the intensity in a perpendicular direction compared to the branch. So this helps us recreate the weight matrix that we want. So this is the weight matrix used in the computational model. So this is our target. You see here that 1 should transmit strongest to 5 and 3 to 7, etc. We put everything in a waveguide to keep the light inside. Something I forgot to mention here, that the dipole pattern also sends light out from the inner layer, which is important because we need to communicate with the next layer that will eventually be situated on the perimeter here. Here's results from our modeling. So this is an intensity plot at the communication wavelength. Here we see the dipole pattern and that most light is absorbed by the opposite component. This is the weight matrix that we get, and it's fairly close to our target. And this is the emission pattern from one device. So when we combine this with the Python model, we take our simulated weight matrix and our simulated activation functions. We plug this in to the ring attractor in the computational model, replacing the mathematical functions and matrices that were there from the start. We actually get some really good navigation and model results. So even though that our activation function is now 2D and is an explicit function of both the excitation and inhibition currents, we get good results even for doing this a repeated number of times and adding noise to the activation function result. We see that our network performs well even up to root length of over 2 and 3,000 steps with added noise of 20%, which is quite much. So to summarize, I would like to show you two slides here. One that compares our solution to photonic solutions. So using light as a communication bearer of information is very energy efficient and fast. And using nanowires keeps the evaluation losses low, as these devices are small intrinsically. We have estimated our cost per operation at about 100 attojoules per operation, and this is actually on par with the human brain. Here we compare the footprints of our complete network solution with that of a nanophotonic chip, and you see that our footprint is quite small. And with that, I would like to thank you for your attention.